Hi, Chemstars. It's me, Gerund. Don't believe anything the corgis told you. Cats rule, dogs drool. We're gonna go over some combined gas laws today. Remember, I don't have thumbs, so I'm gonna do my best. Don't wait to be great. Good girl. Okay, what an excellent guest lecturer Gerund was. We're going to go over combined gas laws today. This puts together everything we learned from Boyle, Charles, and Gay-Lussac. So we actually can manipulate pressure, volume, and temperature. There's 6 variables in this equation. You will always know or have a way of finding 5 of those. So we're only ever solving for the one unknown. So here's your combined gas law equation. Remember, every time we start with that equation. And we also can never use Celsius or Fahrenheit. It has to be Kelvin because we don't want to have 0 degrees or negative degrees. So we're always going to add that 273.15 Kelvin. So here's problem number 1. Remember, this should already be done. You should be checking work with me now. Gerund believes in you, so no cheaters. The initial pressure of neon gas is 1.5 atmosphere. Label that pressure 1. Initial volume is 3.0 liters. Label that volume 1. Initial temperature is 20 degrees Celsius. This is T1, but make a note, we've got to convert to Kelvin. What is the new volume? So we are going to be solving for V2. If the pressure increases to 2.5 atmospheres, that's P2, and the new temperature is 30 degrees Celsius, that is T2. Oops. And we want to make a note, we're going to have to convert that to Kelvin. Okay. So first things first, it's always the same with all these problems. Always, always, always write that initial equation. Don't skip it. It's probably the most important step. Once we have that initial equation, then we're going to go through and we're going to substitute. So we want to look back to the top. P1. What is P1? Oops, hold on. Okay, there we go. So what is P1? From the problem, P1 is, hold on. Uh-oh. What? Struggling with the touchscreen today. Okay, well, we're going to do this. P1 is 1.5 atmospheres. What is V1? V1 is 3 liters. And T1 we have to convert from 20 degrees Celsius. T1 is 293.15 Kelvin. Okay. So what's P2? P2 is 2.5 atmospheres. V2 is an unknown, and T2 wow, T2 is not cooperating. T2 is 303.15 Kelvin. Okay, so this might look a little bit scary at first, but all we have to do is do some algebra to isolate and solve. You can do that algebra however you like, as long as we're isolating and solving V2. You could cross multiply and divide. You could take one thing at a time, bring this up to the top, bring this up to the top, divide that one out. Whatever you're comfortable with, as long as you do the same thing to each side equal sign, you're doing algebra. So whenever you do your algebra, here's what we end up with. V2 is equal to 1.5 atmospheres times 3 liters times 303.15 Kelvin all over 293.15 Kelvin all over 2.5 atmospheres. If you check and look, we have atmospheres canceling out, we have Kelvin canceling out, we're left with liters. That's a good double check to do before you start working your calculator to know that we have the algebra correct. The unit should cancel and leave you with the liters for the volume that you want. So you plug that into your handy dandy calculator of science, and your calculator says 1.86140. That, of course, is too precise. We've got to go back and round to our least number of sig figs. So let's look at the original problem. 2 sig figs, 2 sig figs, 2 sig figs. Now I skipped the Celsius Kelvin ones because technically when we convert to Kelvin, we're conserving the least number of decimal places, which would be 1. That actually gives us 4 sig figs, but that's more than 2. We have to go to 2. So 1, 2, look to the right. Does the 6 round the 8 up? Yes, it does. Final answer is 1.9 liters. Good job, you finished your first combined gas law practice problem. Gerund is proud of you. Okay, let's go to problem 2. maybe if my smartboard will cooperate. Problem 2. Initially, a sample of xenon gas, oh boy. Initially, a sample of xenon gas has a volume of 750 milliliters. Now notice that we're in mils, not in liters here. And a temperature of 0.0 degrees Celsius. Make a note, that's T1, we've got to convert to Kelvin. To convert to Kelvin, we just add that 273.15 to 0, and we'll get 273.15. The pressure is unknown, so P1 we don't know, we're solving for P1. The final pressure was measured at 99 kPa, kilopascals. The volume decreased to 550 milliliters. That is our V2. Now, if you look right here, we've got mils and mils. That's fine. These equations are all proportional to each other, so whatever unit we put in is the unit we're going to get out. Later, when we do the ideal gas law, we'll have to be more careful with that, but here, since they're the same, we can go ahead. And the temperature increased to 25 degrees Celsius, but we do have to get that to Kelvin because we can't ever have a 0 or a negative in the denominator. What is the initial pressure? So again, we're asking for that P1. So let's plug in what we know. Okay, P1 is unknown. Initial volume is that 750 milliliters. And T1 is 273.15 Kelvin. From the problem, P2 is 99 kilopascals, kPa, V2 is 550 mils, and T2, we need to take that 25 plus 273.15 Kelvin, and then get our answer. So this is the correct setup. All we have to do right now is we are trying to isolate and solve for P1. So how do we do that? We have to do some algebra. So this is just your Algebra 1 type stuff. So I want you to rearrange, isolate, and solve. And so what do we get for P1? When you rearrange and isolate, you get 99 kPa times 550 times 273 all over 298.15 times 750. Before you plug into your calculator, double check your units. Milliliters on top cancels with the milliliters on the bottom. Kelvin on the bottom cancels with Kelvin on top. We're left with kPa, which is what we want. Pressure is going to be measured in kPa. So plug all this into your calculator, take everything on the top multiplied, divide by everything on the bottom, and your calculator will tell you 66.51246 kPa. Too precise. How many sig figs do we want? 2 sig figs here. That 0 is a placeholder. 2 sig figs. Don't worry about the sig figs here. Technically, we had more than enough. We had like 4. So we're going to go to those 2 sig figs. So 1, 2, look to the right, the 5, we'll round the 6 up. Our final answer is 67 kPa. Okay, and we've got one more problem on this page. Let me extend the page a little bit so we can get it in the middle of the frame here. A balloon is filled to a volume, that's V1, of 1.5 liters at 15 degrees Celsius. That's T2. Or, that should be T1. My bad. Let's fix that right now. That should be T1. Make that T1. At a pressure of 850 millimeters of mercury, what is the new volume V2 at STP? Now remember from your notes, we learned that STP means standard temperature and pressure. That standard we've decided as a community is 0 degrees Celsius, which is 273.15 Kelvin, in 1 atmosphere. Well, we're in millimeters of mercury, so go back to the first 2 pages of your homework and notes. 1 atmosphere is the same thing as 760 millimeters of mercury. So in our problem, write down the equation first and plug in and solve. P1, pressure 1 is 850. Volume 1 is 1.5 liters. And temperature 1 is 15 plus 273.15, which is 288.15 Kelvin. Pressure 2, standard, is 760. Volume 2, we don't know, we're solving for. And temperature 2 is 0 degrees Celsius, or 273.15 Kelvin. So do your algebra, isolate and solve, and here's what you should get V2 is equal to. V2 is going to be 850 times 1.5 times 273.15 all over 288.15 times 760. If you look, the millimeters of mercury cancel, the Kelvin cancel, and we're left with liters. So we can go ahead, plug that into your calculator, and you'll get 1.5903. But how many sig figs? 1, 2, 1, 2. 2 sig figs. 1, 2. Look to the right. What will the 9 do to the 5? It will round up to 1.6. Good. We finished the first page of gas laws, combined gas laws. Let's go to page 9. I'll go a little bit faster. If you get confused or stuck, just pause the video, look back at your algebra and your notes, and you'll be fine. Okay. A cave has been discovered filled with methane gas. The volume of this cave is 125,000 liters. That's our V1. Its pressure is 780 torr. The methane is trapped, brought to the surface, where the volume has been increased to 150,000 liters, that's V2, and the pressure is 880 torr, that's P2. Just remember that torr is like essentially the same thing as millimeters of mercury, at a temperature of 75 degrees Celsius. So that is going to be our T2 right there. What is the temperature in the cave initially in degrees Celsius? Okay, so that one's a little bit trickier. We're going to work through this step by step. So P1 V1 over T1 equals P2 V2 over T2. Pressure 1 in the cave, we were told, is 780 torr. Volume 1 in the cave was 125,000 liters. And temperature 1, we don't know. Pressure 2 at the surface from the problem, they are telling us that it is 880. Volume 2, the gas expanded. Whoa. What happened? Volume 2, this is new. Okay. Volume 2 is 150,000 liters, and T2 is 273.15 Kelvin plus that 75 degrees Celsius. So 348 Kelvin. So we have all of our variables except for T1. This one, it's going to be easiest for you probably if you cross multiply and divide to isolate and solve. So when we do that, we take T1 times 880 times 150. That's one side of our equation now. And that's going to be equal to 780 times 1250 times 273.15. So I've cross multiplied and divided. So how did we get T1 by itself? We did the cross multiply. Now we've got to divide. So divide these terms out, and we get that our work, T1, looks like this. So what's our calculator answer? Our calculator answer is 257.15625 Kelvin. That's not what the problem asked for. It asked for what's temperature in Celsius. So we've got to subtract that 273.15. We get negative 15.99 degrees Celsius. Okay. Last thing is round for sig figs. 3 sig figs, 2 sig figs, 2 sig figs, 2 sig figs. Least number of sig figs is 2. So this is either 260 Kelvin or negative 16 degrees Celsius. Okay, problem 5. A propane tank has a volume, initial volume V1 of 15.0 liters at a pressure of 1.35 atmospheres, P1, and a temperature of 12 degrees Celsius. Remember, convert to Kelvin. What is the new pressure? So what is P2? If the volume is expanded, the gas gets bigger to 25 liters, that's V2, with a new temperature of 30 degrees Celsius. Remember, convert that to Kelvin. Okay, so remember, we're going to always start with our initial equation, P1 V1 over T1 equals P2 V2 over T2. We're going to isolate, or we're going to substitute. Then we're going to isolate and solve. So let's reveal what all of our substitutions should be in one moment, as soon as my smartboard stops acting. So here, P1, V1, and T1, I showed the work we're taking to 12 Celsius plus 273.15. Then we don't know P2, we do know V2 and T2. Take that 30 Celsius plus 273.15. We need to get P2 by itself. Do your algebra either by cross multiplying and dividing or just doing the same thing to each side. Here is your work for what P2 should be with all the variables plugged in. So let's take a moment and let's check to make sure all of our units cancel. Atmospheres does not cancel. Liters cancels. Kelvin cancels. That's good because pressure we want in atmospheres. Plug it into your calculator. Calculator says 0.86113 atmospheres. Look back to your problem. 3 sig figs, 3 sig figs, 3 sig figs. Temperature is weird, but when we add these up, we conserve decimal places, so it actually has 3 sig figs. So our final answer, we want 3 sig figs. Decimals present, start at the first non-zero on the Pacific. That means 0 is a placeholder. 1, 2, 3. Look to the right. Will the 1 round the other 1 up? Nope. Final answer is 8.61 ATM. Okay, problem 6. A scuba tank puts 125 liters of oxygen into a 5... Now, humor me, make this 5.00. I want to have more sig figs in this number. And plus, scuba tanks aren't like about 5. They're exactly 5. Initially, the pressure of the gas is 1.00 atmospheres and is pressurized to 10.0 atmospheres. If the initial temperature was 28 degrees Celsius, T1, remember, convert to Kelvin, what is the temperature, so what is T2 while in the tank? Initial equation, always start with that. Then we want to substitute, we'll cross multiply, and then we'll divide, and we'll figure this out. Okay, so pressure 1, we're told, is 1.0 atmospheres. Volume 1, 125 liters. Temperature 1, we were given as 28 degrees Celsius, added to 273.15, you get 301.15 Kelvin. Pressure 2, they told us the tank was pressurized to 10 atmospheres, and they told us it was compressed down into 5 liters of volume. Remember, we're cheating here. I'm going to say it's actually 5.0. It's a very precise number. We know exactly what that is. And T2, we don't know. We're trying to solve for. So we're going to cross multiply, and when you cross multiply, let me extend the page to get this into our frame. When we cross multiply, for some reason, part of it got erased. Oh, that's weird. Huh. T2 times 1 times 125. So we're taking this term, multiplying together. That's the new side of our equation. And then we're multiplying the other side. This side, that's the new part of our equation. Okay, so we cross multiplied and then we have to divide. So we're going to do that work over here. So T2 is going to be equal to this side divided by what's left over. Plug that into your calculator. You get 120.46 Kelvin. However, they gave us a temperature in Celsius, so it doesn't specify, but you usually report back in the same unit that you're given. So we're going to subtract that 273.15, and we get negative 152.69 degrees Celsius. Then all we have to do is round for sig figs. 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs. That's why I added the extra zeros here to 5. We want a precise number. Scuba diving is very precise. So we're going to round to 3 sig figs. So 1, 2, 3, that's going to round to 120 Kelvin. And make sure we put a point at the end to make that 0 significant. So 1, 2, 3, decimal, it makes it significant there. Or 1, 2, 3, look to the right, 6 rounds 2 up, negative 153 Celsius. Okay, so we're done with the combined gas law. Come back next time to learn about the ideal gas law. Bye guys, don't wait to be great.